The first thing that we need to know here, the aim is band gap of semiconductor. Okay, so we are taking a p-type material and an n-type material, extrinsic materials. So p-type material ఏముంటుందంటే let's say this is conduction band, this is valence band. Fermi level will be nearer to valence band in p-type material, and the excess holes that are coming from the dopant will be nearer to valence band. The energy of the excess holes coming from the dopant, trivalent impurity నుంచి వచ్చేటువంటి carriers అన్ని కూడా they are nearer to valence band. Okay, whereas in n-type material the excess electrons will be nearer to conduction band and Fermi level lies near to conduction band. This is a band diagram for p-type and n-type materials. Okay, so when you join them, when you try to form a p-n junction, these energy levels will balance, Fermi levels will balance up, and what you left with is this. So this is the valence band on p side, this is the conduction band, this is the Fermi level. So Fermi levels will balance up and the valence band remains as it is, conduction band remains as it is. I mean, everything will shift up on p side and everything will shift down on n side. So this is a p-n junction. So here you will have holes and here electrons that are coming from the dopant element. So now I am giving a bias to it. Let's say forward bias. I am giving positive potential on p side and negative potential on n side. What happens? So these electrons will be pushed to the other end, and these holes will be pushed to the other end. And when you give energy, electron will rise up in the conduction bands and holes will sink down in the valence band. So they are just like plastic balls in water. So when you give energy, they will move down in the valence band. More and more energy, they will move more and more deeper into the valence band. Okay, so what happens? So as long as you supply enough amount of energy sufficient to cross this barrier, there won't be any current. So once you supply enough amount of energy, beyond that current starts. So let's say this is 0.7 volts, this side is 0.7 volts, this side is 0.7 volts. Okay, so if you supply sufficient amount of energy, then these carriers will reach the other end. Current continues. Okay, then what about reverse bias? Same band diagram. These are holes, these are electrons, and I am supplying negative potential on p side and positive potential on n side. Holes will come outside, electrons will come outside, so no current will pass across the diode. No current will flow across the diode. So then, where from do we get that reverse current? So minority carriers ఎక్కడి నుంచి వస్తాయండి?
ఆటోమేటిక్గా హోల్స్ అనేవి మైనారిటీ క్యారియర్స్ కదా సార్.
So where from do you get holes? ఎక్కడి నుంచి వస్తాయి? వీటికైతే అడ్రస్ నేను చెప్తున్నాను. These are from the dopant element. Where are the other carriers? Minority carriers ఎక్కడి నుంచి వచ్చినాయి?
కాదు సార్.
ఎక్కడి నుంచి వస్తాయి అంటున్నాను. ఉంటాయి అంటే
ఎప్పుడైతే కరెక్ట్ ఫ్లో ఆ మెటీరియల్లోనే ఉంటాయి కదా సార్ కొన్ని.
ఫ్రీ ఎలక్ట్రాన్స్ గురించి మాట్లాడుతున్నాం. ఐఎమ్ నాట్ టాకింగ్ అబౌట్ బాండెడ్ ఎలక్ట్రాన్స్.
డోపింగ్ చేయడం వల్ల ఫ్రీ ఎలక్ట్రాన్స్ వస్తాయి.
P side only dopant gives you holes. Electrons ఎక్కడి నుంచి వచ్చిన P side?
ఎక్స్ట్రాగా హోల్స్ ఉంటాయి కానీ ఎలక్ట్రాన్స్ వోల్టేజ్ కాదు. ఎక్స్ట్రాగా హోల్స్ ఉంది సార్ చెప్పినట్టు ఎలక్ట్రాన్స్ లేవు కదా ఎక్కడి నుంచి పొటెన్షియల్ కరెంట్ వస్తుంది. అంటే మనం ఇవ్వడం వల్ల వచ్చినట్టు సార్ మధ్యలో డిప్లీషన్ రీజియన్ క్రియేట్ అయిన తర్వాత సర్టెన్ అమౌంట్ తర్వాత ఆగిపోతుంది.
Where from do you get electrons on P side and holes on N side? They are from the intrinsic material. Whatever carriers I am showing here are from the dopant element. But the base semiconductor made of silicon or germanium will have a proper band gap. And if you supply sufficient amount of energy equal to the band gap, electron hole pairs will be created. From the dopant element you get either only holes or only electrons, whereas from the base semiconductor you get electron hole pairs. Okay, so let's say if these are 1000 in number, these are 5, very less in number compared to the dopant elements. So what I am showing here is the energy gaps and carrier energies. So on y-axis you have energy here. That's a graph. So on y-axis you have energy. I am showing energy related to, let's say if I have some 1 million. So what is the doping concentration usually? What is the doping concentration? ఎంత కాన్సన్ట్రేషన్లో డోప్ చేస్తారండి? పీ టైప్ ఎన్ టైప్ డోపెంట్ చేస్తారంటారా? ఎంత కాన్సన్ట్రేషన్? 1 in 10,000. 1 in 10,000 at least. So 1 in 10,000 silicon atoms are replaced by aluminum, let's say, or gallium. Okay, so doping concentration varies from 10 power 4 to 10 power 6. So 1 in million or 1 in 10,000. So now I am showing here the energies related to all the base silicon atoms as well as the dopant elements. So I am considering 1000 dopant atoms. So that means base atoms ఎన్ని ఉంటాయండి? If at all doping concentration is 10 power 4, how many base atoms I am considering? Let's say silicon. I am doping or I am replacing 1 in 10,000 silicon atoms with aluminium, and I got 1000 aluminum atoms. So how many silicon atoms are there? For each 10,000 silicon atoms, there will be one aluminum atom.
Each 10,000 ki one aluminum.
So I got 1000 such aluminum atoms. So how many?
10,000 one aluminum.
కౌంట్ కౌంట్ ఉంటుంది కదా,
ఏంటి సార్?
కౌంట్ ఉంది కదా.
అంటే ఇందాక కూడా అన్నాను కదా డోప్డ్ ఆటమ్స్ ఇంట్రిన్సిక్ మెటీరియల్ నుంచి అని చెప్పి అలా ఏం ఉంది కదా డోప్ 10 lakhs అవుతాయి కదా సార్ అప్పుడు సిలికాన్ ఐటమ్స్ అన్ని మీరు చెప్పిన రూల్ ప్రకారం 10,000 కి
1 crore ఉండాలి మొత్తం. ఇఫ్ దట్ 1000 ఇన్ నంబర్,
100 కాదా సార్?
1000 into 10,000 కదండి.
1000 సార్ 100 కి
1000
1000 అయితే 1 crore అవుతుంది సార్. 1 crore.
సో ఓకే, టోటల్ ఒక 1 crore సిలికాన్ ఆటమ్స్, బాండెడ్ సిలికాన్ ఆటమ్స్ నుంచి ఐమ్ పికింగ్ అప్ 1 సిలికాన్ ఆటమ్ అండ్ రీప్లేసింగ్ ఇట్ విత్ అల్యూమినియం. సో అలాగా ఇప్పుడు నా లాటిస్ మొత్తానికి ఎన్ని ఉన్నాయండి? 1 crore సిలికాన్ ఆటమ్స్ నుంచి ఒక 1000 అల్యూమినియం ఆటమ్స్ ఉన్నాయి. ద సేమ్ స్టోరీ అప్లైస్ on the other side also. Out of 1 crore silicon atoms, I am replacing 1000 phosphorus. Okay, and I am showing the energy levels of all those set of atoms. ఏమొస్తుంది? So this is the base energy level of silicon, silicon valence band and silicon conduction band. And my dopant atom energy levels are these 1000. So energy of all the 1000 holes will stay at this level. Let's say this is 10 electron volts, and if this is 11 electron volts, this may be some 10.1 electron volt. The same way here also 10 electron volts, 11 electron volts, 10.9 electron volts. So energy of all the electrons from phosphorus will require very less amount of energy to send them into conduction band. So if you supply just 0.1 electron volts of energy, they'll simply go into conduction band. Okay, so the current in forward bias is mainly due to these carriers, the carriers from the dopant atom. So the energy you are supplying here is only sufficient for this gap. That gives you the gap between the donor level and the conduction band. Here the gap between acceptor level and the conduction band. So if you measure the gap during forward bias, or whatever energetics, if you measure the energetics during forward bias, all the information that you get is only the gap between the donor level and the conduction band. Okay, so if you reverse bias it, all the dopant carriers will simply come out. They won't give any contribution to the current. And now the carriers are coming from the base silicon atoms. They exist both on p side and n side. The carriers are coming by thermal energy. So when you supply sufficient amount of temperature, heat, they take that heat energy and bonds will be broken in silicon atom, and you get electron hole pairs. So on p side in total you have, let's say, 1005 holes and 5 electrons. And on n side 1005 electrons and 5 holes. Okay, so count wise, on p side you have electrons as the minority carriers, and on n side holes are the minority carriers. Here electrons are the majority carriers, 1005. కౌంట్ చూసుకుంటే అంతే కదండి. ఎక్కడి నుంచి వచ్చినంతకి? ఇంట్రిన్సిక్ సెమీకండక్టర్ మెటీరియల్ నుంచి థర్మల్ ఎనర్జీ తీసుకొని జనరేట్ అయినటువంటి ఎలక్ట్రాన్ హోల్ పేర్స్. ఓకే, so you have holes here and electrons here. 5 in count. So you have holes here and electrons here. So this I am not showing because these are from the intrinsic material. These are minority in number, very less in number. Okay. So now if I see this, so I am applying negative potential here. What happens? These carriers will move downwards. These carriers will move in this way, upwards. So it is very easy to move a hole upwards and very easy to move an electron downwards. ఎందుకనండి? I mean, they are just considered as a plastic balls in water. You can easily move them up. You don't need any additional energy. Right? Here also you don't need any additional energy. Whatever energy you supply, the current starts immediately. And the current is controlled by temperature. No other choice. So the number of carriers generated here are only by temperature. Right? So in reverse bias, current starts immediately and the value remains constant. Whatever may be the voltage you apply, current starts immediately and the value remains constant. So let's say this is at room temperature, and for other temperatures you may get more number of carriers but the current remains same. I mean, value remains constant. So you may get a higher value with rise in temperature but the value remains constant. So now the amount of, so the carriers are now generated by breaking up bonds in the valence band and taking them to conduction band. So whatever current you are measuring is a result of transition of electron from valence band to conduction band. Right? So you will get a measure of band gap in reverse bias. So whatever energy you are supplying here is now gives information about the band gap. Whereas in forward bias, all the information that you get is only the gap between donor level and conduction band or acceptor level and valence band. This is the only gap you get from the energetics of forward bias. Right? So now the number of carriers in any excited level at a given temperature is given by Boltzmann equation, and is n naught e power minus Eg by kT. Okay, so these are the number of carriers between any two energy levels. Let's say n naught are the number of carriers in ground level and n is the number of carriers in excited state. The number of carriers is given by, so let's say when t is equal to 0, what happens? When t is equal to 0, zero na infinity na, e power minus infinity. What is that value? E power plus infinity is infinity, minus infinity 0. This is when t equal to 0, number of carriers in the excited state is 0. So ఏమవుతుందండి ఈ పవర్ దీన్ని ఎట్లా రాయొచ్చు n naught by e power infinity, that is n naught by 0, n naught by infinity 0. So when temperature is 0, number of carriers in the excited state is 0, and as the temperature rises, what happens? So when the temperature rises, this whole term will reduce, and since it is a negative exponential, this whole term will rise. అంతే కదండి. with rise in temperature Eg by kT, this number will reduce. This is the negative exponential. So e power minus అంటే ఏంటి 1 by e power n. సో ఆ నెంబరు పెరుగుతూ ఉంటుంది. That number will rise. So overall number of carriers will increase with rise in temperature. So if you rise the temperature, number of carriers in the excited state increases. And that is what entirely contributing to the current here. So current ఏమవుతుందంటే I is Q by T, number of carriers by time. So if you introduce time into this equation, you get I is equal to I naught e power minus Eg by kT. Okay. So ఇప్పుడు ఇందులోంచి వేరియబుల్స్ ఏంటి, కాన్స్టెంట్స్ ఏంటి? What are the variables and what are the constants? K is a constant. E is a constant. T variable. I naught is a constant. I is a variable. So ఇప్పుడు ఇందులో డిపెండెంట్ వేరియబుల్ ఏంటి, ఇండిపెండెంట్ వేరియబుల్ ఏంటి? Which one is dependent and which one is independent? Which one is in user control and which one depends on that particular one? So T is in user control, and by tuning T you can control I. So T is independent variable. I is dependent. Okay, so whenever you do an experiment, you have to tune that independent variable and see how that dependent variable changes. T vary చేస్తూ ఉండాలి. So on x-axis you should take a function of T, and on y-axis it should be a function of current, whatever may be the function. That part we need to see. So now our ultimate aim is to get the value of Eg. So we need to bring out that Eg from this equation. Eg ని బయట తీయాలంటే ఏం చేయాలండి? Okay, so if you take logarithm, what happens? Log I is equal to log I naught plus log e power minus Eg by kT. Base E as usual. So log I is equal to log I naught minus Eg by kT log E base E. So we'll be left with log I is equal to log I naught minus Eg by kT. This almost looks like a straight line equation. The form y is equal to mx plus c. So here 1 by t takes the role of x. Eg by k is the slope minus Eg by k. Log I naught is c. So you have a negative slope here. So if you draw a graph between 1 by t versus log I, you get a straight line with positive y-intercept and negative slope. So this y-intercept is positive and slope is negative. So what is that slope?
Minus Eg by kT.
So if I draw a graph with 1 by kt, life will be even more easier.
Easier.
So I'll be left with minus Eg as the slope. Okay. So we have to consider, I mean, the most important correction in the previous session was we have to consider the temperature in kelvins. So 273 plus 23, let's say we'll start from 300 kelvins and go up to, let's say in the steps of 10,
Yes, sir. 80.
300 to 400 kelvins. Start from 300 kelvins and go up to 400 kelvins in the steps of 10. So 300, 310, 320, 330, 340. It's like that. Vary the temperature and measure the current. Okay. So that part we will see in TINA, that Texas Instruments network analysis software. Okay. So construct the circuit and measure the temperatures. Current for various temperatures. Then we will see the program to fit the curve and all.